Hi everyone, today I'm here to talk about using sewer models to determine trade waste contributions to downstream corrosion. Before I start, I'd just like to acknowledge Graham Hamer and Joseph Cheska from Jacobs, who are also involved in this work, and Heath Georgia from SA Water. So today I'll just give you a bit of a broad context on sewers and corrosion, and then I'll move on to a trade waste investigation we did for SA Water, going through the objectives, the methodology and the results, and then I'll make some general conclusions and hopefully we'll have some time for questions. So the largest proportion of a water utility's asset value is in their pipes below the ground. Sydney Water alone has 27,000 kilometres of sewer pipes and 695 pump stations. And in Australia, there's greater than 110,000 kilometres of sewers. And these are worth tens of billions of dollars. So as you can imagine, sewer maintenance costs are significant and ongoing. But the good news is there's been a significant increase in the understanding of sewer corrosion mechanisms in the last decade, and we have a better ability to model and predict sulfide corrosion rates than ever before. So how does corrosion happen in a sewer? If you've got septic conditions in the sewage, the sulfates in this sewage can be reduced to sulfides by sulfate-reducing bacteria that live in the walls, in the biofilms on the sewer walls. This results in the emissions of corrosive and odorous gases, of which H2S is the major one. This H2S is then oxidized by H2S oxidizing bacteria that live in the crown of the sewer, producing sulfuric acid, which then leads to corrosion of concrete sewers. It's important to note that the H2S uptake changes based on piped material. Concrete's a very good sink and accounts for loss of H2S from the headspace through concrete corrosion. Conversely, in plastic line sewers, there's no H2S uptake, and the H2S moves along the sewer till it's either released or taken up by downstream concrete. So the ability to be able to model sulfide corrosion in gravity sewers and understand where this will occur is a key factor in the long-term asset management of sewers for water utilities. So what are these sulfide generation models useful for? Well, we can predict the level of sulfide generation, how it moves from the liquid to the vapor phase, how the airflow moves through a sewer, the biochemical corrosion mechanisms, and we can also look at the effectiveness of sulfide control chemicals. So now moving on to the SA Water trade waste investigation. The project came about because a trade waste producer approached SA Water and requested that they be able to increase the BOD in their discharge. So SA Water needed to investigate the impacts that this change in the discharge licence would have on the downstream sewer. So they engaged Jacobs to determine the contribution that discharge from the trade waste producer had on downstream corrosion and sulfide levels, and to investigate options for minimising the impacts on the sewer from any changes to the trade waste discharge licence. So this sketch here just shows you the configuration of the sewer that we were looking at. So the trade waste was discharged into a 4.2 kilometre rising main, which then flowed into a 2.2 kilometre vitreous clay gravity main, and then that discharged into a pump station. So the section of interest was the vitreous clay section, although its doesn't corrode itself. There were 15 concrete manholes along that section which were susceptible to corrosion. So now I'll just go through our methodology and results. First, we collected data and did some sewer sampling, and I'll talk about that on the next slide. Then we produced a calibrated model of the existing system using Jacob's interceptor model, and we fed the sampling results into this to calibrate it. And then we used the model to predict impacts from trade waste changes and assess the potential corrosion rates and what controls could be put in place to minimise impacts of this change in discharge licence downstream. So the data collection considered the trade waste discharge parameters, the sewer design, the materials of construction, and the current sewer condition. And one thing that was very important to consider was the potential presence of other significant trade waste producers, because we didn't want to assign corrosion and sulphide generation from them to the trade waste producer we were interested in. In terms of sewer sampling, this was undertaken to make sure that we captured the discharge from the trade waste producers. So we had to look at the times and discharge patterns for when this occurred. Then we took 6 liquid phase grab samples over 48 hours and analysed those for dissolved sulphide, pH, temperature, conductivity, dissolved oxygen, oxidation reduction potential, BOD and sulphate. And we also undertook H2S logging in 5 locations. We then produced a calibrated model of the existing system and then used it to predict the trade waste contributions to sewer corrosion using 2 methods. Firstly, we assigned domestic characteristics to the trade waste flow, and secondly, we removed the trade waste flow altogether. So you can see here in this plot on the right, which shows the corrosion rate along the length of the sewer. Initially, with the trade waste discharge in place at its current levels, the corrosion rate was estimated at up to 8 millimetres per year. Once we changed this trade waste component to either domestic flow or took it out altogether, the corrosion rate decreased significantly to less than 3 millimetres per year. The reason that putting the trade waste in as domestic flow had the lowest corrosion rate predicted was because this allows for some dilution, whereas removing the trade waste flow altogether doesn't do that. What we found was that the trade waste producer had a significant impact downstream and accounted for about 30% of the dissolved sulphide, 83% of the H2S and 60% of the corrosion. So you can see that some form of control at their site could have a significant beneficial impact for the sewer. And the reason that the H2S levels the contribution was much higher than the dissolved sulphide is that there was a lot of turbulence generated in the discharge main from the discharge manhole from the rising main, which caused the sulphides to move to the vapour phase. These modelling results can also be useful for utilities to allow them to assign some of the costs associated with downstream corrosion and odour mitigation back to the trade waste producer. So after we'd worked out the contribution from the trade waste producer, we then looked at altering the trade waste discharge in the model to determine whether it was okay to change the licence requirements or not. So we looked at 3 different levels of BOD, 1,000 milligrams per litre, which is what their current licence requirement was, and then we upped this to 2,000 and 3,000. And as you would expect, the H2S and corrosion levels increased as the BOD increased. What we then did is we increased the BOD, but also increased the pH as well to reflect an increase in alkalinity. And what we found is that by increasing the BOD and the pH together, we could bring the H2S concentrations down significantly. And you can see in this graph here, the yellow and the light blue plots at the base with the lowest H2S concentrations occurred when we had the increased BOD and the increased pH. So we concluded that increasing the pH had a greater impact on the corrosion and H2S levels downstream than increasing the BOD, which was good news, because what we found is, so our conclusions were, if the BOD in the trade waste was increased, then the producer must also elevate the pH levels sufficient to overcome the fermentation in the rising main and the dilution effects of incoming flows. And if this higher pH was maintained in the downstream sewer, they'd be able to control sulfides, keeping them in solution and minimising corrosion and potentially odour problems. So as you can see, this modelling was really useful to provide SA Water with an indication of the controls that were required at the trade waste producer to enable them to increase the BOD in their discharge without causing detrimental impacts on the downstream sewer. So from our work, we were able to conclude that accurate modelling of the sewers does allow utilities to proactively estimate the true costs of changes in trade waste licences on their assets. This allows the utilities to determine whether the costs on assets are acceptable from a risk management and financial perspective, whether they think control measures are required, and then if those financial costs should be passed back to the trade waste producer. These models are also useful to the trade waste producer because they can decide if it's more cost effective to further treat their trade waste at its source prior to disposal, or whether to contribute to the costs associated with corrosion and odour control in the network. When using modelling similarly to how it was used in our project, it's really important that the time is taken to configure the model so it reflects reality as closely as possible. Sampling of the existing system is a really important step in achieving this and provides valuable data for model calibration. So as you can see, a proactive approach to trade waste management benefits both the utility and the trade waste customer, avoiding the negative impacts of corrosion on a utility's assets and odour on the surrounding community. So with that, I'd like to say thank you for listening, for staying up late or getting up early, and I'll have a bit of time for any questions. I'm sorry, I've just seen my son walk past behind me on his way to school. So I just saw a question from Jeff Mann asking, did we calculate airflows as well? Yes, we did look in the modelling that we did, looked at the ventilation rates through the sewer in working out the sulfide generated in the liquid phase and in the vapor phase and how that moved through the sewer.